Hello everyone, my name is Richard O'Hagerty. I'm a postdoctoral researcher from University College Dublin. And the study I'm about to present is focused on the performance of highly insulated walls. So building regulators are consistently specifying reduced U values for building components in an effort to reduce the energy consumption of buildings. This consequently means more insulation, but are these regulations sufficient, or indeed are they actually too stringent? And how accurately do these theoretical values describe the in situ behaviour of building components anyway? This paper aims to address some of these questions. Specifically, it aims to understand how accurately theoretical thermal transmittance calculations represent actual building performance, and what are the knock-on effects of overestimated performances. To begin with, we need a metric to compare the performance. Here we use the U value and the thermal conductance. The U value is typically used in Europe and is a measure of the thermal transmittance through a building's component, roof, wall, window, etc. It is commonly calculated theoretically following a relatively simple process to which there exists an international standard, as shown in the left. To calculate the design U value, one needs the thermal conductivity of the materials used and the thickness of the various sections, as well as the surface resistances. The thermal conductance does not include the surface resistance, which themselves become almost negligible in highly insulated building envelopes. Thicker and lower conductivity insulations will give you lower U values. The in situ U value, on the other hand, is physically measured. It is far less common to do such a measurement, primarily because of the difficulty and time involved in doing it. So both methods are used in this study, and the difference between the theoretical and measured performance is compared. Before presenting our own results, I want to show some of the results from the literature. To compare the difference between theoretical and measured performance, we might plot a graph that looks something like this, where you have the theoretical U value along the x-axis and the difference between the measured and theoretical value along the y-axis. If we monitored a house with a design U value of 0.25, for example, and then we actually measured it, and we found it was also 0.25, we'd get a point here in the graph. But what if that U value was actually 20% higher than the designer calculated, and therefore losing 20% more heat than was designed for? We would get a point here instead. And if we found that it actually performed 20% better than the designer calculated and had a lower U value, we would get a point here. So I've had a look through the scientific literature over the past decade that compared in situ with theoretical U values, and I've found the following. So, a few things to see here, but each point here represents a single test, and I've colour coded each point by the study from which I extract the data. There are two very interesting things to note here. The first is that at lower U values, the percentage error appears to be greater. And secondly, that in almost all cases, the designer has calculated superior U value than what was actually measured. So I suppose, just to emphasise again, all these points above the x-axis are cases where the measured performance was worse than design performance, and those points below the x-axis are cases where design U value is underestimating the actual performance. In this study, we measured the performance of two almost identical nZEB wall build-ups, as shown here, using the exact same international standard method. First, we calculated the thermal conductance values based on the thermal conductivity and thickness of the various sections, and we found that both had particularly low U values, as shown here. Further, we modelled the performance of a 113 metre squared sample dwelling, which had nZEB specifications, and found that both had very low space heating requirements with these given specifications. Both are almost identical as well, just because the wall build-up is so similar. We then measured the performance at two locations in the wall by measuring the inside and outside temperatures, as shown by the red and blue lines. Red for inside and blue for outside, red warm, blue cold. And the heat fluxes as shown by the grey and black lines. The reason we measured at two spots was to ensure that the measurement was accurate. You can see here both the two red lines and the two blue lines and the black and the grey all match up, showing that we are actually getting a representative part of the wall. So it's hard to tell directly from these graphs what the thermal conductance is. In order to do so, we need to divide the heat flux by the temperature difference. When you do this and accumulate the results over time, the plots start to converge. It is at at these convergence points, and after meeting the criteria set out in the standard, that you can obtain the U value or the thermal conductance. From doing this, you can immediately see the difference in performance of the two walls, despite their almost identical theoretical performance. To summarise these results, you can see in this table that the in situ or measured performance was 232% higher than the theoretical measurement for nZEB, and only 13% higher for nZEB. So in nZEB, something is going on there. To compare the impact of this poor performance, the embodied energy of each insulation case was compared as a function of the amount of thermal resistance it is providing. So on the y-axis we have primary energy required to achieve a thermal resistance of 1 meter squared Kelvin per watt for 1 meter squared wall insulation. You can see here that in the case of nZEB, the amount of embodied energy per unit of thermal effectiveness is more than 10 times that of the theoretical estimate and of nZEB. So in conclusion, we found that there's a big gap between the theory and in-use performance. Specifically in the two case studies here, we found that one performed very poorly, almost twice as bad as was theoretically calculated, while the other one was worse than was calculated, but only slightly worse. This poor in-use performance means that the more carbon is actually invested for a given use, so you're not getting the same functionality out of the insulation, so you're investing more carbon for a given functionality. This means that payback periods are extended, so in fact you're possibly investing more carbon in the insulation than what is actually saved in operational energy. And that then draws up the question of, should we focus more on strategy and actually continuously lowering our U values? We need to ensure that when we specify low U values, we actually achieve them. And on that note, I'd like to thank you for your time and have a good day.